Okay. Let me just see if these folks could hear me. Hey, we got one more person. Is everyone here now? I got another note of someone at the door. Is Alex here?
Yeah.
Okay. Okay. Anyone? Okay. All right. So James, you hear me. Antima hears me. Whoever else is remote. Sahil, I think, is remote, and everybody else is here. So again, I'm recording this, and what I had mentioned to the folks here, I just want to give a little bit of a overview of what we're going to be looking at in terms of today's class. So let me just pop up a schedule here just so we see what's going on. So we're going to do a little bit of a review. Again, we got a little bit of a late start, but I think we're fine. So I don't expect we're going to talk too much about the data structures. So we're going to do an introduction into the DOM, which is going to be a very quick lecture, and then we're going to do a workshop, which is selector. I guess this is scheduled for a while. We've got here 10:30 to 1, and then 2 to 3. Which is good. I think it might be a little bit more time than you'll actually need to do it. There'll be a little bit more of recursion. I know that there were some questions about recursion, and we'll talk about it. I want to do a couple of examples of recursion. I've started to notice something very simplistic, and I mentioned it. I put up a video on the binary search tree, and that is like figuring out recursion for a very simple example and then trusting the recursion. So like taking the example of a binary tree where you have just one node and a left and a right, and seeing that recursion works in that simple case and saying, hey, look, if it works in that simple case, then just keep on going through with the recursion. It's going to work for a more complex case. And we'll look at that. I have a very simple example of flattening an array and 2 different ways to do the recursion. I want to do that with you so you're comfortable with it. There's another example of recursion in this selector workshop. And again, there's actually 2 different ways that you could end up doing it. So you'll get even more comfortable with it. So we're going to do the selector, and that's going to take us into this afternoon. We'll take some time to figure out what we're going to do for lunch around here. And then we're going to go into sorting, which is I think a really good one. And we're going to talk about sorting. We're also going to talk about big O notation, so the complexity of 2 different sorts, and to try to calculate how complex an algorithm is. And so you'll get a little bit of a feel for that, of how expensive some of these computations are, how that bubble sort is going to be something that's going to feel very sort of brute force-like, and it's going to be pretty high complexity, and we'll find out that when we end up doing a merge sort, it's going to be a lot easier to do. And again, even with that, we're going to do a little bit more recursion. Not that you encounter recursion all the time. You do from time to time, and it's nice to know that you have a handle on it. But it is something that people like to ask on job interviews, and frankly, it is. The more that I program, the more important the more I realize how important it is. So that's what our game plan is for today, and we've got some other lectures tomorrow. So just to sort of know what's on tap for tomorrow, we're going to do my favorite workshop, which is Game of Life. which some people know about. I didn't know about it beforehand, but it's this whole idea of having a board with certain squares that are considered alive and how they end up propagating, how they stay alive through successive rounds based upon what their neighbors are around them. And I really like it because I think it, first of all, it's a real working example. It's a game to some degree. Not a game, but more of a demonstration. And I like it because I think it pulls together a lot of the things that we've been doing, some functional programming, and also working with the DOM, some other things that we're going to look at. We'll get a chance to use some bind functions, you know, with, again, the sort of three ways of controlling context, which are really critical, the idea of calling and applying and binding. So we're going to look at that in that workshop, which is great, pulling some of these things together. And then we're going to look at getting into Node and how the Node ecosystem works, if you haven't done it before, how it's different from JavaScript. And we're going to build a little Node shell, so that we're going to write a Node program that's going to allow us to do things like find out the files in a directory, like an ls command, a cat command, a less command, and we'll see how we could get that working and then sort of dry things up so it works a little bit better. So, and the other part about that is that for the first time, really, we'll get an idea of, maybe the second time, but how asynchronicity works. And we're going to run into that all over the place, you know, with JavaScript. Since JavaScript is single-threaded, it becomes incredibly important. So that's what the game plan is. One thing we could do now, do people have questions about data structures? I mean, one thing I can do, if you want, is I can pop up our repo. Wait, someone downstairs? Wait, Jason? What else are we missing? Ah, okay. All right, so this is let's pop our library up here.
Eric, now if this is outside the scope of what you want to talk about right now, it's totally fine. But
you know what's outside the scope? I don't want to talk about any conversations about things that are outside the scope. No, I'm just kidding. Go ahead.
It's about what you just mentioned, right? So I have a conceptual question about asynchronicity and recursion, right?
Okay.
So they're contradictory, pretty much, right?
No. Later.
They're unrelated.
Mm-hmm. You know, look, recursion is something calling itself over and over again, and that has to stop at some point. Right. Asynchronicity is something that's going to happen in the future. So the most, well, we use promises to deal with asynchronicity. But I mean, you could I'll give you a very simple example of something that's asynchronous. If we go and wire a button on the DOM, and we say, hey, look, when this button gets clicked, call this function, right? That's asynchronous, okay? Now, that's an example of something that's asynchronous that might never, ever happen, right? If a user never clicks on that button in the DOM, it never happens. So, you know, that's a very simplistic form of asynchronicity. There's another idea. If you end up setting a timeout and you say, hey, look, I'm going to have this code run in 2 seconds, right? That's also asynchronous. But really, when we start to think about asynchronicity, I think a better example, let me just raise this because my back is really bugging me today. Hello. So when we think about things that are asynchronous, a good example is in Node, when you go to do things when you're dealing with, like, the file system, when you go to read a file, right? And the way that those modules are working, they don't want to starve the Node process, which is single-threaded. So that, you know, the way that works is that, hey, look, there's another process that's going to go, and that's going to go read a directory or read a file. And when it's done, it will end up calling this function. And what it comes down to is that you're giving up control, right? You're giving up control to another process, and you're saying, hey, look, call me when you're done. Promise is sort of, it's still asynchronous, but it just makes it easier to manage things that are asynchronous by, in essence, I think, wrapping them in promises. And we have 2 great workshops on promises that'll really help you understand that stuff.
The thing that I think the thing that if JavaScript is asynchronous, how does recursion lock the file? So if I recurse and I have 3 functions, let's say.
Right.
And I recurse out to myself.
Right.
But my next action, right, is function 2.
Function 2 will never get called till function 1 is done. So if you have something that's going on, I mean, that's not asynchronicity, right? Okay. No, because I mean, what'll happen is that I think really what you're going to end up doing is you're just going to be, you're never going to make it to that second promise. You're going to, excuse me, you're never going to make it to that. You know, when your recursion is done, then you'll end up going whatever the next line of code is.
I mean, that makes sense. I mean, obviously that makes sense.
Right.
I just don't, if that function, if the current iteration of that function is really asynchronous, why should it have to wait for the promise? Why should it have to wait for
I'm assuming that there's no asynchronicity in that recursion. I'm assuming that the recursion is just calling the same function over and over again. If there was some asynchronicity in there, then you have something else to deal with. Usually, I have to say, you could. I mean, you could have asynchronicity with some form of recursion where, you know, I could think of, I did something recently where we did something with Sequelize, where we had objects that we were putting permissions on. And so literally like these JSON objects, we would say, hey, look, are you allowed to see this object? But it wasn't only are you allowed to see this object, but are you allowed to see other objects that are within this object? And it was asynchronous because you wouldn't know whether or not you had the permissions. You might have to make a call to something else to see if you ended up having these permissions. So it was asynchronous, but you treated those things really separately. But we'll see when we end up getting into that. It's a good question. So let's talk about, or if you guys have questions about it, this was our binary search tree. And so this was some, I mean, I think the thing to look at initially, right, the most important thing is the idea of inserting, right? I mean, if you can't create a binary search tree, then, you know, you're not going to be able to search by breadth or depth or whatever else you're trying to do. So, you know, the thing here is that this is the whole idea of thinking about it simplistically, and then again, I think that this whole idea of sort of trusting the recursion. Again, if the recursion doesn't work, you're going to get an infinite loop. You'll know it doesn't work pretty quick. But if we sort of take this example here, and we look at it and say, you know, take the example where you have a binary search tree that you're inserting to, and that's the only node. It doesn't have a left or a right. Okay, so if you look at that, you could say that we are going in here, and by the way, I'm not even, this size I guess is correct, but let's sort of forget about that for a second. You end up going in here, you find out the direction that you're going to go in, right? If the value that you go in with is less than the value of the current tree, you know you're going left. Otherwise, you end up going right. Okay? If it turns out that there's nothing in that direction, right, it's empty, you're done, right? You ended up going in and inserting this binary search tree, and you're done. Okay? Otherwise, you say, hey, look, all right, I know the direction I was supposed to go in. Okay? Let that be the guy that does the work, right? Hey, I can do it myself, if my left to right, if I'm going to be, and if not, then I ask the tree who is blocking, you go to do it. Go ahead.
Yeah, there's just a quick syntax question. I see you're using the direction as a string that you access with square brackets.
Yes.
Is that equivalent to saying like this dot left?
That's exactly what it is, and it's a pretty common thing. So with JavaScript, what it comes down to with JavaScript and objects is that JavaScript objects, one thing we know about JavaScript objects is they have keys and they have values, okay? And we can access the properties with those keys by dot syntax, or we can access it with brackets, okay? When would we have to use brackets? When it's variable, that's true. How about if we have a name that has some weird spaces?
Yeah,
Okay.
I was just going to bring that up. I got tripped up on previous practice problems myself, and then when I did the hash, I was using dot notation and go down into objects, and I got screwed because some of the keys had a number in them. It was like
Or
something.
it's got, well, let's rephrase it, right? You can use a dot syntax if it's a valid variable name. That's it. Okay. If it's a valid variable name, in this case, we could use the dot syntax, but here I just, my code's a little bit more concise.
Right.
I mean, you could start out and say, hey, look, if I'm going left, if there's nothing on the left, do this, right? Otherwise, have the left insert. If I'm going to the right, there's nothing on the right, insert on the right, okay? Or have the right one insert. But this just makes it, and again, it's also one of these things where when you get things to work, you might not start out with the square brackets, but then you look at it and you say, hey, look, these two things look totally identical aside from the words left and right. And that's when you start thinking about where it might make sense to use the square brackets. So square brackets are very common. And you know, the other thing here is that the square brackets, I mean, if you look at it, this is the property of an object. And the property of an object can be a simple type, simple value type. It could be a number. It could be a Boolean value, okay? It also could be another object. A function is another object. So there's nothing that prevents me from using those brackets and then, you know, in this case, now left is just an object, but then I say insert, right? Insert is a function, and I could end up calling that function. So again, it's just two different ways of accessing the keys of an object, right? What you end up doing with that key depends on what the key is, right? If the keys are totally fine, okay? If it's not, don't use parentheses because it'll say it's not a function and you'll end up getting an exception, okay? So again, the thing is here, if you think about it with that very, very simplistic example, then you go to yourself, all right, well, let's say that I am going left and there's another node on the left, okay? So in that case, what you would end up doing is you would end up, so you go in here, you see that you can't go left, you then go left, okay? You end up going left. Again, it's gonna, so in our case, if we have something that's on the left, then we have the left insert, and you could say, well, you know, what if it turns out that, you know, I've got to go left, and then I look at the value, and then I have to go right. Well, again, if you just sort of think about, you know, if I can't do it, okay, if I can do it, I'll do it. If I can't do it, I'll tell the node that I'm going in that direction to do it. And then just trust the recursion. I think that you know, helps me a lot. I mean, you have the same thing with, I think I did it the same way with contains here. And again, I did another thing here, which was maybe even a little bit more simplistic. I think that this is almost a little bit more complicated. Let me just see if I could pop something up real fast. One of the things that I wanted to do yesterday, and I recorded this because I think it was, again, I just wanted to make this, nothing else. You have a little bit of time to kill at some point. Go and say, let me see what it's going to take for me to implement the binary search. You know, it's not, again, whether or not now you know what you need to do. You don't have to necessarily go in with a spec, you know, you don't necessarily have to go through that workshop to do it. You could go and do it on your own. If you don't know where to start, then go through the workshop. But if you know, hey, look, let me just see if I can create a binary search tree. Let me see if I could create a linked list, right? Let me just see if I could create a queue. Do a couple of things that you know the queue is supposed to do, and do a console.log, or in my case, I ended up using Testum with a very simplistic test. I mean, you know, sort of compare this to the workshop, which is a lot more detailed. I have my tree results, I have a binary search tree, and I say, hey, look, I want to have a traverse method where I pass in a value and I push the value here, and I expect the results to be in order, which sounds very much like a depth first, right? Is that right? In order, yes, in order. Okay. So in this case, you know, I think I'm going to get the results in order. I want to see contains equals true for 6, and contains for 99 is going to be false. So again, this is just so easy to do with Testum. If Testum is installed globally, you can write a very, I mean, this is about as simplistic as I think you could get to some degree. And by the way, you could start out with just the insert if you wanted to, and just test out that if you ended up saying, you know, tree dot left dot value is going to have some value, you could do that as well. But when I went to implement this, I tried to make it even a little bit simpler here. So like, for instance here, starting out with the insert. So I put a couple of methods here that I found I was reusing. So I have a couple of methods on, again, this might not be in your spec. These, by the way, might not even be methods that you have the desire to expose to someone that's hanging onto your tree, in which case you don't have to make them private or hide them or anything like that. You could, if you wanted to, if you didn't want people to use get direction, put an underscore in front of get direction. By convention, people that see an underscore there, that's you know, someone that's using what would in this case be your API, something that's wrapping around your code, they would know not to use it. But in this case, it's, you know, breaking this up into some very simple methods. Getting a direction, I pass in a value. If the value, if my value is less than, if the value that I'm passing in is less than my value, I know I'm going left. Otherwise, I'm going right. And then I've got this can go. And the can go, have you guys seen the not operator at all? The not operator just takes a truthy or falsy value and actually turns it into true and false. And the way that that works is, just imagine that there was something going in that direction. That's an object, okay? Objects are truthy. So when you say not the object, you get something falsy, okay? You get false. And when you end up saying not false, you get true. The same way, if something is undefined, okay, not undefined is true, not true is false. So not is just a way of turning something, you know, if it says, hey, look, I don't want to deal with this truthy and falsy. I want true, I want false, which is totally legitimate. I want a Boolean value, okay? I don't want JavaScript's sort of light, fluffy, truthy, and falsy. Not ends up doing that for you. So, you know, here I find out whether I could go in a certain direction. And then when I go to insert, I get my direction for the value. I find out if I could go in that direction, okay? So in my case, if I can go in that direction, that means there's a node there, right? Because that's what the can go ends up doing. If I can end up going in that direction, okay, meaning there's a node, then I just tell that node to do the insertion. Otherwise, I'm free and I create the binary tree. You can see an insertion really, you know, breaking my methods out these things become 3-line methods.
Can you just flip back to your for a second? Go to the contain. So in this one, on the other one you just flipped out of, in the contained method, you did return recursion, and in this one you didn't.
Yeah, I don't like this method. And the reason why I don't like this method, you know what it feels like to me? It feels like, in this method, that I'm looking at all the values. Like, I'm basically running my traversing. I'm traversing every node in this thing. So even if I found my value at the top, I think I'm still traversing. This is not a good implementation. The other implementation is better.
So it's best practice to have a return.
Well, let's take a look and see why there's a return. Let's think about why there's a return. So here, there's no return because I'm basically using closure to store whether or not I found this thing. This function gets called with every node. So this is bad. I'll correct this. I mean, it worked, but it's not great. Because basically, if I did a console.log here and I realized I had, 1,000 items in my binary search tree, this would end up hitting every one of them, right? As opposed to this, if I did it correctly. So this one, if it turns out, so this is, right, so now sometimes you do recursion where you don't necessarily care about the return value. And again, this is another case of, I think, trusting the recursion. So in this case, let's think about a very simplistic case. I created a binary search tree with a value of 10. I go in there and I see if it contains 10. I'm done, right? I go in there, I have a binary search tree, right? Let's just think about this for you. Without drawing a diagram, just thinking about it. I've got a binary search tree with a 10 and a 2, right? So 10 is going to be my binary search tree. 2 is going to be on the left. So I go in here, I say, well, is the value equal to what went in here? It's not, so I don't return. Can I go in the direction that I want to go in? Okay? If I can go, right, if I just have one node, then of course, it's going to end up returning false. If I could go down in that direction, okay, what I do here is that, so if we had a 10 and a 2, right, I couldn't find it here, I then say to my left node, hey, left node, do you contain? And so it goes in, now it's going to go in and it's going to call that method again, okay? It's going to go in there and that method is going to return true, but I want to return true from this outer node, okay? But in this case, instead of actually recursing the entire tree, which I don't have to, when it finds out, it'll be done. And again, I think the way to do it is to think about it with, don't think, hey, what if I'm 10 levels down? No. If it works 2 levels down, it's going to work 10 levels down, right? There's nothing that would prevent it from doing it because it's just building up the same pieces. Because if it works 2 levels down, then I go down one level, and then I'm just going 2 levels down again, right? So if you just see it works going down 1 level, again, just trust the recursion, but you have to do the return, because if you don't do the return, it's going to go in here, and it's going to call something, but I'm not going to be doing anything with the value that it returns, so I would end up getting back undefined.
So basically, if you don't want to iterate over the entire collection, you would use a return?
I think you're going to be forced to use a return. I think you're going to have to.
You don't need to.
You don't need to if you're iterating over the entire collection. I don't think I have a way. I mean, you can also take the case, well, let me use depth first, but let me exit depth first when I find what I'm looking for. I don't even know how the hell you'd really do that.
If you wanted to say, like, instead of contains, like, how many there are.
That's a different story. Then you want to return. That's exactly right. If you wanted to sum everything up, then you want to traverse everything. So I think when I first looked at this, I said, I think I had done the depth first, and I said, oh, great, I could find out all the values, and I could put them, I think initially I probably thought, well, let me put all the values in an array and see if it's in the array. And then I said, well, let me just use closure, and I'll just find the value. I don't need to put anything in the array. Just looking at it now, looking at these two examples, this is a much better solution. And again, if you want to know why the return is there, just think about two levels, right? Because it wasn't there on your first one, it's going to be there on your second one. You went into the call stack on the second one, okay? And if you didn't end up returning anything, right, you would go in here and this value would be undefined, right? So in other words, the contains method has to return something. That's why the return's got to be there in all cases.
So that's essentially the base case?
The base case, I think, is here. I think that's
Right.
the base case.
Right.
I mean, base case. It's yeah. I guess that's I would say that's the base case. I mean, I could maybe think a little bit more. Sometimes it's not totally clear exactly what sometimes it's pretty clear what the base case is. When we end up looking at sorting, it's going to be very clear what the base case is. We're just controlling. There's no while loop in here, but we can see that we're not calling ourselves. And again, the whole idea here in this case is that everything's a tree, right? So when we say recursion, it's not necessarily like, think about this for a second in this example. Not that this is critical, but it's not like you're necessarily calling the same function every time. I know it feels that way, okay? But really what it is that you're having other objects call their function, okay? Now it turns out that they all share the prototype. So yes, officially it is the same function. But really what you're doing is you're telling me, hey, look, if this object can't do it, okay, have this child object do it until you run out of room. Either you found it or you run out of room, one or the other.
A lot of times when I think about recursion, I also think about it in terms of the loop, because it's really just, you can implement it using a loop as well. And you just think about it as, okay, every time I want to go through the loop, I'm either going to store a value or I'm going to change my reference point to some other reference point.
Yeah, or else you'll be stuck in the loop.
Start the loop.
Right. Like I tell you, we would be, what would put us in a loop? I guess what would put us in a loop? Let's say I got rid of the DIR here. All right? So if I could go left, great, but let me try this node again that I'm on.
Yeah.
Right? So this is the same as changing the reference, right? It's the same thing.
Yeah, it's just with a loop, you need a lot more code.
I think that's probably right. I think that's probably right. But we are going to do stuff with we will be doing some recursion with while loops as well.
Is there a case where it's useful to know what your parent is?
Well, I mean, it could be useful.
Like maybe in deleting, or I don't know.
I don't know. I don't know the answer. I mean, it's by definition, I think the answer is no, right? You only sort of work your way down the tree. Working your way up. I mean, look, again, these are used for indexes and searching, right? So you're splitting the difference of where you want to go. I mean, it's like when you use the index of a book, right? You go in and sort of find a letter halfway in until you find it.
But you could be doing an operation like, give me the average of myself and my parent. You know, if you didn't want to had to do something like that, then you could use parents.
Right, but I think it just might be a different type of structure, right? It just wouldn't be a binary search tree. The whole idea of that is again, you want to be able to find what you're looking for by splitting the difference. That's the whole idea of being able to get to something very quickly. And again, I think what it does in the back of your mind, aside from it being a bit of an academic exercise and learning these things about JavaScript, in the back of your mind, you say to yourself, hey, this is cool. When I start doing stuff with a database and I put an index on the first name of the user table, well, it's not magic, right? There's some B tree that's sitting out there that's controlling this, and you could then make a little. Yeah, look, I think base makes you conscious of the fact, okay, what are the ramifications of me? Because I know that if the data is changing a lot, these indexes are going to have to get updated. And so you sort of, if you get into situations where you're fine tuning things, you say, well, what's slowing this down? Well, do I need all these indexes? Or that sort of thing. Because someone who's a real novice would go either no indexes or, hey, let me index everything. And, you know, you can imagine, you know, indexing some of this stuff just wouldn't make any sense. Go ahead. Oh, you go.
Yeah, just a quick note on recursion. I don't know if it's helpful to anyone. I always think about the terminating cases first. So, like, what is going to make my recursion end? Like, so in this case, if you find a value that matches, you know you're done.
Right.
And if you're at a node where you have to go left but you can't go left, or you have to go right but you can't go right, you're done.
Then you're done. That's right.
And then the other part is actually might be the easier part, because the rest is you're just calling yourself.
Right. But you have to, you know, it's that part. I really feel it's that part of just, once you have those other cases, right, it's just trusting that, yes, it's going to work. It's a little bit of a leap of faith, but I say, for me, and again, everyone's got different ways of helping with this. Write these enough and you'll figure it out. But again, the whole idea of just do a couple of things. You don't have to think of something complicated. And if it works just with a couple, then, you know, again, if you're down one level, then you're, again, just working with a couple, right? In the end, so you'll see how that works.
Can you explain a little bit further about how this would relate to an index?
So I assume, and again, I'm not a database expert, but my assumption is that the way that indexes work is there are B trees that are set up so that you could end up finding something pretty easily by, hey, look, this is what I'm looking for. Well, is it less than this? Okay, to go down to get to find out where that record is in the database.
If I had a really simple set of columns, 2 columns, one was an auto, and then index it down, and I index that, just 1 to 100. You're saying that you would create a binary search tree with 50 as the...
I don't know. I'm not sure. I don't know how it works. What we will do... Yes, and it very well might be, but there is something balanced about the way that it works, right? It's not, I don't think it's just a hash table, because you always see how these things end up, or at least I've seen, that they're set up as B trees, which would lead me to believe it's some kind of balanced tree that's set up. Yes, we will be doing something called, again, some of you might know a hell of a lot more about databases than I do, and it's worth looking into, and you guys, at some point, you guys are going to do some tech talks. That's another thing. So that's a topic to sort of throw out that we could look at. And I think that one of the things that we'll do is we're going to do something called FQL, which is going to be sort of our JavaScript, our own kind of implementation of searching through JavaScript objects, functional query language. That's what we're calling it. And when we do that, we're going to create indexes by, like, let's say we wanted to index the genre of movies. So we could basically group together all of the genres and say, hey, look, for horror, these are the indexes where you're going to find these movies. But I think that a balanced tree, a B tree, does something a little bit more complex. That's my guess, especially if you have a huge table and there's a lot of different values. There's something about, hey, look, start here, look here to get you close to where you're going.
Yeah, the idea of the B tree is like to minimize the number of times you access the hard drive.
Right, or to get to the page that you're looking for, that sort of thing. Okay, I think, so we did this, you know, I think that the hash table one, and again, maybe I'm wrong about this. I thought that was, I mean, in some ways, I thought that was a little bit easier to implement. I don't know how you guys felt about it, or if you ended up getting to it. So this is, just go up one level. You know, this, if you look at this logic, the whole thing, I think that gets to be a little bit tricky. So you know, for this, I think you just have to work in pieces. If you understand how a linked list works and you're confident with your linked list that you can add to the tail and search for something, then I think you're pretty good, right? So the key thing here is a linked list where the linked list value is going to be a key value pair. Okay? That's what it comes down to with this implementation. Okay? The linked list value, so a linked list is going to have a value, and that value could be anything. When we did the example with linked lists, we did values that were user objects. So there's nothing that prevents us from having an object that's going to have a key and a value. So if you think about the idea of, and I think setting is kind of an interesting one here. So when we go to set the value, first of all, there's some error handling. If the key's not a string, we're specifying that the keys have to be strings. If the key's not a string, we end up throwing an exception. We then hash the key to get a numeric value that will get us to where we're going pretty damn quickly, okay? And again, think about this like the drawer of a file cabinet. So at this point, we know where we're going in the array. We look to see, can we find something at that position? If we can't find something at that position, what I'm going to do here is I'm going to assign, and I don't know if you've seen this, but this, you always start from the right and go to the left. Create your linked list, assign it, and put it in the variable list. So in this case, the variable list is going to contain your linked list. Okay? And I could have maybe optimized this a little bit, because if I just created the linked list, there's no reason for me to actually look for anything at all. But I've got this method, get key value, from the, so in here I'm passing in both my key and my hash, and I think I did that because I'm using this a couple of different places. So I go in here and I'm using this two different ways. So hey, look, if you pass me the key and you don't have a hash, I'm going to go ahead and compute the hash. And all I was doing was building this method to say, look, if you hashed it already, if you hashed your key already, fine. I'm not going to, let's just pretend that for some reason that hashing algorithm was expensive. So if you already have the hash, fine, give me the hash. If you don't, I'm going to compute the hash. So this syntax is also pretty common, which is the OR syntax, and basically what it says. What I'm doing here, and some programming languages let you do it, but what I'm basically doing is assigning a default value. And I think ES6 allows you to define default values, but that's all I'm doing. Okay, if you passed it in, great. If you didn't, I'm going to hash it. And I go and I look at my memory. I see if I have a value there. If there's no list there, then I just return. Otherwise, I end up searching the list. And I search the list with a, I basically loop over the list. I get back, again, since anything I'm inserting in the list is a key value pair, to find out if I have that key value pair, I just basically find out if my key value pair's key is the same key that I passed in. And so if we, and I'm using this at two different, go ahead.
How come you don't have to write var hash equals hash?
Because I think in that case you'd be overriding. I think you would be overriding it. The variable exists. It exists when, so one of the things that happens when you call a function and you end up saying this is my parameter, you have a variable already.
Yeah, it's defined in your function, your parameter.
Yeah, behind the scenes, JavaScript is going in and saying, all right, I see a parameter here. I'm going to do var. And in this case, if you don't pass a value in, it gets a value of undefined. But it exists.
Yeah, well, the thing is, by nature of the fact that it's declared in the function, it's scoped in that function.
Mm-hmm. That's exactly right. So, and in this case, if I go up here, I see if I could find the key value pair. If I found it, it means it's already in there. What I'm avoiding here, and this is a little bit of a subtle thing. Actually, the last time I did this workshop, I didn't even realize this. What I want to avoid is I want to avoid my linked list having 2 keys that are the same. Okay, 'cause that's just going to screw me up, right? I want to make sure within a linked list, my keys are going to be unique. So I see if it exists. If the key, I don't care about the value. Okay, I just want to get that key value pair. If I can get that key value pair equal to the value that's going in, otherwise I just add it to the tail. Okay, and that allows you to set something.
Going back to that method. So what is KVP here?
So what's happening here is that now this is the way that our linked list is implemented. Okay, our linked list has a search method, and the way that we've created that search method, maybe when we specified, we said, hey, look, with the linked list, when I search for something, okay, either I can pass you in just a simple value, or I could pass you in a function. And when I pass you in a function, you're going to return me that value if this function that I pass in here, that function, okay? I'm not calling that function. The search method within the linked list is calling that function. And if you go back and you look at the code for the linked list, you'll see that what will happen is that linked list will run this function. If it gets a true value after running this function, it'll return that linked list, that particular node's value.
So obviously, right, the KVP it's an object.
KVP, again, this is just the nature of, so what I say is I say, hey, look, I built this object.
No, the input. I mean, the input on that function, KVP, it's an object, right?
In all, yes, it doesn't have to be.
No, I just mean in the code.
No, you're right, though. You're right. And sometimes you look at this, I think a natural inclination to say, where the hell did KVP come from? But again, this is the whole idea of when you think about the linked list, I wrote an API for a linked list, right? And I say to you, hey, look, you want to use it? Give me a simple value. I'll return the value. Or give me a function. And what I'll do is for every node in the linked list, okay, I will call your function with the value of that node. And by the way, when you use a linked list, you don't know what the hell a node is, right? You don't really end up getting exposed to these nodes. You end up just inserting items in the linked list. But internally, I say, hey, look, I will iterate over all the items, okay, or whatever. I'll use magic, okay? But give me a function, and magically, if that function ends up returning true, okay, that's the value that you'll end up getting. So again, what I'm trying to do is that from within the linked list, all I want to do is find the one, okay, that has that particular key. So there's 2 APIs that are going on here. There's the API for the linked list, okay, and there's the API for the hash table. But go back, look at the linked list again, and you'll see that search function, and that's why that works the way it does. You could maybe implement it in other ways, but it's nice to tie these things together. You know, some people said, well, can't I just put a hash in that spot in the array? And it's like, yeah, you could, but you could have also just used a hash from the beginning. I mean, it sort of defeats the purpose, right? We could have just used JavaScript hash object for a hash table as well, and could have done the same thing, right? So, you know, let's pretend that we don't using our linked list. So when we go to get something, it can't be easier, right? When we go to get something, in this case, we have a key, and in this case, I haven't computed the hash already. So I just say to my linked list, here's the key, and it goes in and it uses this method again, sees if it can find it. If it found it, if it doesn't find it, I return it, okay? If I find it, again, since my linked list is important and confusing, since my linked list, what's inserted into the linked list is a key value pair, okay? The item that I get back when I find it is a key value pair, in which case I return the value. So this is a lot. There's no real recursion or anything like that that's going on here. These are straight lines, right? When you think about recursion, I think you think more of trees having recursion. DOMs, which we'll see, will have some recursion. But here a linked list is linear, and our array is linear. So that's the that's the implementation of this. So let's wrap this up. I think we went a little bit, maybe longer. Okay. Let's see what we got here. I got to set my cursor up correctly.
He's asking, hey professor, how does hashtable.js know to look in the linked list?
Oh, that's a great question. And the reason why it knows how to do that, that I copied. So I also have, let me see, I've got our, go up one level here. Here's our library. Here's our data structures. The reason why it works is that it's in the folder. And it's just the way that Testem works. The way that Testem works is Testem basically includes all the files. And the way that JavaScript works is that Node. But the way that JavaScript really works in the browser, and that's really what Testem is doing, is that this function linked list is available because it's just sitting right here. And I bet you if we ended up going in and looking at how Testem works, Testem, my guess is what Testem does is probably loads all the files in the directory and then loads all the ones that have spec after them. I bet you if you looked at it, you can go and look and see how Testem works. I bet it's kind of interesting.
I think it loads in the
It might, but the specs I bet you loads after because it probably needs to have the other ones first. Right, right. I think it doesn't. I think the specs. I think there's no order based on. You're right. Probably loads them alphabetically, but probably spec second. Yes.
And it also depends on where you're running. If you're running in a root directory or sub directory.
I think Testem is going to operate on the directory that it's in. I don't know if Testem takes into account subdirectories, but I think there's a setting in Testem.
Pull script from another directory, then you need to run it in the root directory.
Okay.
That's what it said.
Yeah, I've just used it sort of within the context of this class, but that could definitely be true. We could look at the documentation of that. Go ahead.
I know you covered this a little bit, but
Well, then why ask me, John? Go ahead.
in the get key value pair
Right.
function where you have list search and then you have the KVP parameter,
Mm-hmm.
where is it pulling that parameter from? Is it this within the function?
Okay, so this is. Let me pull this back up. So this is this is in hash table, right?
Hash table line 37.
Okay. So yeah, you know what? I think I did this differently, a couple of different places. What was I looking at before? I was looking at. Let me see. No, I think it's the same thing. So you're talking about this, not.
No. Right above line 32.
22.
32.
Okay. What's the question?
Where is the parameter pulling the object from? Is it equal to this in the greater function? How is it setting KVP?
Okay.
Call the function or call that object on that function.
Okay. So this is a critical thing. Okay. This has to do with the way that the linked list is implemented. Okay. I built this linked list function. And I said with this linked list function, hey, look, if you want to find an item in the linked list, pass me a function, okay? I will call that function, and when I call that function, I will pass an object, okay? It's going to be the value of in your linked list. I'm going to loop over every value in your linked list, okay, until I find what I'm looking for. If I don't find what I'm looking for, I'm going to end up returning undefined. So again, I don't know if this helps, but I could call KVP whatever I want to. But the logic here is predicated upon the fact that I know what I put into that linked list. And what I put into that linked list, again, the linked list doesn't give a crap what you put in it, okay? You could put Boolean values in your linked list. You could put strings in your linked list. You could put objects in your linked list. Your linked list couldn't care less about it, okay? But when you go to search, you care. And so that the linked list says, hey, look, I don't know how to find what you're looking for. If it's just a simple string, I know how to do that. I know how to do equality on a simple string or a number, okay? But if what you're searching for is an object, give me a function. I will pass you your object, and you tell me if it's the right object. And I'll know it's the right object because when I call that function, it will end up returning true.
Well, yeah, I mean, I get that part that it's calling search on. Never mind.
The thing is, you know, my implementation works.
Right.
My implementation of search wouldn't work because I was calling it passing function, the value, not the current node object.
That's right. That's
So
right.
mine
So
would
you,
fail. Actually,
right.
mine would work.
You made it. All right.
Mine wouldn't work.
So
No,
Into
it's
the parameter.
search. When you're searching.
yeah, I mean, we could go take a look.
It's iterated, that's where it's called.
That's where it's called.
And KVP equals the current object.
Yes.
And let's
Calling it on the list, that's your point.
let's also be careful with the pronoun. I don't know if that's what it is. But when you said when it calls search, okay, it's not calling search. We're calling search. Okay, we have the object and we're calling search on the object, and we're passing in a function which is going to allow the search implementation to work. So you have to sort of see who's calling what. It's very important to do that. All right, let me. I'm going to stop this recording, and then let's take a 5-minute break.